My name is Dr. Marc Taylor. Welcome to Conceptual Physics at Delaware Tech, thinking about physics. So in this pre-unit, we're going to cover a little discussion about how everyday English and physics define different words differently. We'll talk about properties that are measured in physics and the units that are used briefly. Most properties have units associated with them, and the abbreviations for the properties and the units can be very confusing. We'll talk about the concept of proportionality. Is something proportional or is it inversely proportional? And we'll talk about how to use that. And that's a very important concept that will come up over and over again throughout the semester. We'll talk about the difference between scalars and vectors. These are properties that have slightly different characteristics. And a quick word about the math involved and the resources we have. Yes, algebra will definitely help you in this course, but a lot of this course is common sense as well as this proportionality I mentioned. And the formula sheet that you will get, it's a many-page formula sheet. This is your friend, so always have that available. Okay, so physicists have very specific definitions for everyday words. There are a lot of words that we use in everyday English that physicists will use in a slightly different manner. Physicists and scientists in general use the word theory and the word hypothesis in two very different ways. I'm not going to go through every one of these, but to a scientist, a hypothesis is an educated guess. A theory has been tested over and over again and is usually our best explanation of what's going on. Mass and weight are not the same thing. Weight has to do with the effect of gravity on mass, and mass is mass whether there's gravity or not. Speed and velocity. Speed is just how fast you're going. Velocity is how fast you're going and in which direction. So you can see a lot of these words have more specific definitions to scientists. Many of the concepts we're going to use in this course have been somewhat simplified. If we actually went into all the details about what we know in each of these topics, no one would ever learn anything. So we keep it simple, and keeping it simple sometimes means we're just a little bit wrong in what we're saying. Most of the times we know that's correct. So if you do see something that doesn't seem right, tell us. That's fine to bring it up. If it's something that we just simplified, we'll let you know. If it's something that we made a mistake, we'll definitely correct it. And my policy is if you catch one of my mistakes, and there are going to be plenty because I just revamped the entire course. If you find my mistake, I'm going to reward you, usually with a point on your next exam. And you'll find that the more you learn about any field, chemistry, physics, mathematics, biology, the more you realize there's unbelievable complexity involved that's not usually taught in a first semester course. And this doesn't ruin it, but it does make it a little harder to explain to new students. So much of this you probably already understand the concepts of. There's a lot of math you're not going to recognize, but the fact is you'll be surprised at how many of the concepts that we cover in this course actually apply to everyday experiences that you have and will help explain the experiences that you've seen in life that you may have just taken for granted. So let your life experiences help you remember these new concepts along the way. It'll make it much easier to remember. Use them as mnemonics. Common sense will go a long way in thinking about the world of physics, though algebra will definitely help and proportionality will too, which we'll talk about in a minute. There are going to be some concepts that may not make sense at first glance, and even to me, they didn't make sense when I first learned them either, but eventually you understand how they come together. All right, so just a brief look at properties. I don't want you to memorize this list right now. We'll go through these topics one at a time as you progress through the units in the semester. On the left are a list of properties that we might measure. So you have time, distance or length are the same thing. Volume, velocity, mass, force, and weight. Weight is actually the type of force. So is tension, for that matter. Energy, work, and heat are all different versions of energy. And then temperature. And then we have units shown on the right. And there are going to be multiple different units that apply to each item But the important part here is that you have to keep track of the properties versus the units when we go through each of these topics. And this can be a bit confusing for one simple fact. Scientists throughout the ages have reused certain letters of the alphabet for different things. So for instance, if you look at time at the top property, you see it's a lowercase t. But going down, temperature is an uppercase t. We also have another characteristic you'll learn about when we're doing waves called period. Period is how long it takes for a wave to complete, and that is also abbreviated with a capital T. And some of the units are the same abbreviations as different properties that don't match that unit. So it's very easy to get confused. Another point of confusion is weight, which is one of many types of forces. We abbreviate weight as force due to gravity, F sub G, force of weight, F sub W or W. You'll see all of these at different times. But we also use W to refer to work, the work energy, the energy of doing work. And you'll see uppercase W over down in the bottom of the units for watts. So do your best to keep track of the units, and I will do my best to define them as we're using them, and so that you don't get confused. And you can always go to the formula sheet that I prepared. It's many pages, but there's actually a table of properties and matching units with their abbreviations that you can always refer to. So scalars and vectors. So scalars and vectors refer to different kinds of properties. Properties either are properties that only have size, what we call magnitude only. And these would include things like mass. It's a number that tells you how big it is. Is it big? Is it small? Is it 10? Is it 50? Is it a billion? Volume, length or distance, time, speed, energy, power. These are all examples of scalar measurements. They just have size. So what's the other one? The other one is vectors. Vectors are measurements that have both a magnitude, a size, and a direction. In other words, you need to know which way they're pointing. So examples like that are velocity. And you'll see I've got in parentheses, not speed. Speed is what we call how fast you're going. If you just care, oh, I'm going 60 miles an hour. The ball is moving at 20 meters per second. Those are speeds. But if I say 60 miles per hour in that direction, or north, or west, or left, or up, or down, that's a vector. Force and tension are vectors. You always need to know which direction the forces and the tensions are pointing. Acceleration, if you're increasing your speed or decreasing your speed. Scientists use acceleration to mean either one. I know when you're in your car, you use acceleration just to means you're going faster. To a physicist, it means you're changing your velocity. You're changing your speed or you're changing your direction. So it's just a new use of language that you already have been using with slight different definitions. Momentum. Momentum has to do with how much mass you have and how much velocity you have. And since it has velocity as a component, it also has direction. Your momentum's in this direction. Your momentum's in that direction. So these are vector measurements, vector properties. Now, properties, when we're looking at the math and we're looking at the relationship between one property and another property, one variable and another variable, we are often concerned about proportionality. And in fact, scientists work out these formulas that you're going to find because in the past, they realized, oh, this property is proportional to this. And proportional means they both respond in the same way. If I double this, this will double. If I cut this one in thirds, this one will be cut in thirds. And it's always a factor of multiplying or dividing. It's never adding and subtracting, so please don't confuse that. If you see a number has tripled and you know it's proportional to something else, the other number will triple. So properties that appear in the numerator on both sides of a formula are going to be proportional to one another. If there's no fraction, those are numerators as well. They're just numbers where you're not showing a denominator that's really equal to 1. So if one property increases by a certain factor, the other property will increase by the same factor if they're on opposite sides of the equation and they're both on the numerator. Likewise, if one decreases, the other will decrease by the same factor. So for example, distance equals velocity times time, or speed times time. Most of the time I'll use speed and velocity interchangeably, but velocity really means you know what direction we're talking about. So distance equals velocity times time. D equals V times T. Well, D, the distance, is proportional to the velocity. And that little symbol that kind of looks like an alpha, it's not quite an alpha, that's the symbol for proportional. And you'll find that in the textbook, they just use a squiggly line, a tilde, to represent proportional. It doesn't mean approximately. In the textbook, it means, and this is Paul Hewitt's textbook, Conceptual Physics, that squiggle means this is proportional to this other item. So distance is proportional to velocity. If I triple the velocity, I'll triple the distance. If I triple the distance in the same amount of time, I will triple the velocity. So it works both ways. If I cut the velocity in half, I'll travel half the distance. If I travel half the distance in the same amount of time, I will have half the velocity. Again, it works either way. We also have properties that are quote-unquote inversely proportional, and this means that they do the opposite of one another. If one increases, the other decreases, and vice versa. One property, you'll be able to spot this in formulas because one property will be on one side of the equation in the numerator, and the other property will be in the other side of the equation in the denominator. So if one property increases by a certain factor, the other property will decrease by the same multiplication factor. Likewise, if one decreases, the other increases, if they're inversely proportional. So I took the same formula, rearranged it, and solved for time. And now you see time equals distance divided by the velocity or the speed. So time is proportional to distance because it's on the top, but it's inversely proportional to velocity. So you see that symbol T is proportional to 1 over V. That's the same way of saying T is inversely proportional to V. So if you see it on the bottom, it's going to do the opposite on the other side of the equation. So if I triple my velocity and I'm keeping the same distance, my time will decrease threefold. I'm increasing my velocity threefold. I'm decreasing my time threefold. So let's put this together. As I mentioned, most physics formulas over the years were discovered by finding these various proportionalities and inverse proportionalities. And sometimes they're more complicated than the ones I just showed you. But this is a great advantage. It means that if you have the formula, and you do because I gave you many pages of formulas separated by units so you can find everything you need, you can always see right by looking at the formula directly what the proportionality or inverse proportionality is. So for example, here's the formula for gravitational force. This is the force due to gravity, otherwise known as weight if you're just sitting on the earth, but it could be the proportionality, the relationship between gravitational force, the force pulling objects together. Could be one planet and a star, or a planet and a moon, or two planets, or whatever. It's two bodies of any size, but gravity works much better with bigger objects. And this formula says that the force due to gravity, and it's a force, it's pulling in, is equal to some constant g, we're not going to worry about that, times the mass of one of the objects, it could be the Earth, times the mass of the other object, it could be you, the mass of you sitting on the surface of the Earth. And r refers to the distance between the center of one body and the center of the other body. So when you're doing gravity, you don't look at how far, when you say how far you are from the Earth, what you really mean is how far you are from the center of the Earth. And that's how this math works for this. And so r in this case is a distance, and we use a lot of different letters for distance, depending on the context. But r refers to the distance between the two bodies. So if you look at this formula, you've got the force on the left, and you've got on the right side, you've got the two masses in the numerator on the top, and you've got the distance squared on the bottom. So what does this mean? It means the force of gravity is proportional to either one of the masses. So if I change one of the masses, the force will change in the same way. If I change the other mass, the force will change in the same way. But it's also proportional to the product of the force of the masses, excuse me. It's proportional to m1 times m2. So if I doubled both of them, that would be an increase of double for mass 1 and double for mass 2. It would cause the force to go up by fourfold. 2 times 2 is 4. The force is also inversely proportional to the square of that distance between the two bodies that we're interested in. So what does that mean? It means that it's a little more complicated. It means that if the force, if the distance doubled, we would have to double square that number to find out what the force is, how the force changes due to this formula. So if I doubled the formula, we would see a fourfold change in the, double the distance, we would see a fourfold change in the force. If I tripled the distance, we would see a ninefold change in the force, but it would be opposite directions. So if I increase the distance threefold, the force would go down ninefold. If I increase the distance fivefold, the force would go down 25-fold. So you have to square what's happening to the distance to find out what's happening to the force, and because they're inversely related, one goes up, one goes down. So examples, if I double the mass 1, the force will go up twofold. If I double both the masses, as I mentioned before, the force will go up 2 times twofold. And if I triple the distance, the force will go down 3 squared fold or ninefold. And likewise, if I did the opposite would happen. So if I decreased the distance, I made it shorter to 1/3 of the old distance, the force of gravity would actually increase ninefold, 3 squared. So that's how you put these things together. So anytime you see a formula, you can see the proportionality relationships as long as it's all a formula, it's all multiplication and division. Second, you put addition and subtraction in there, you can't use proportionality anymore. But most formulas don't do that in physics. So you have resources if you're getting stuck. We have the lecture videos that I made. You have the slide presentations that I completely revamped from previous slide presentations. If you've taken the course before, I've added a lot more explanation in the slides. We have the textbook, which is very good. There are some small mistakes in different parts of the book. Most of it is because they're simplifying things for you. Because it's a first semester course that's conceptual rather than bogging you down with a lot of math. There's plenty of math still in it, but it's a lot less than it would be in a more advanced physics course. We also have problem sets that are made by the manufacturer of the textbook, so they go hand in hand with one another, and a lot of the concepts are explained in the problem sets as you're doing the problems. We also have labs that might give you clues about how things are related. If you still need help, I have office hours. I'll post those, and you can come to office hours. You don't need to make an appointment, just show up. And we also have the virtual tutoring center that Dell Tech provides. It's open 6 days a week, and I'll post the hours for that as well. There are multiple tutors available. In theory, they should have at least one physics tutor available at all times, but I'm going to try to do tutoring there as well, and I'll let you know my hours if I get them. I gave you the formula sheet, so it's a multi-page sheet that has a lot of formulas broken down by units, as well as tables of units and tables of properties, and even a couple pieces of specific constants that you might need in the formulas. But for the most part, the formulas in the formula sheet, that part of it will be sufficient for your needs. If none of this helps you, I recommend, there are a lot of great videos on YouTube. I'll tell you on the topics where YouTube's not helpful, but it's really only one topic that you see later in the semester. But other than that, YouTube has a lot of wonderful videos to help explain things if you're not getting it from these resources. And then you can always email me. My email is listed here, mg.taylor@dtcc.edu. That's my primary contact. If you need to get in touch with me for an emergency, there's my cell phone number. It's a Los Angeles area code because I used to live there. But feel free to use that if it's an emergency. Emergencies include you can't get logged onto the test and you're running out of time, or there's something failed online and you're getting worried. Don't worry about that. If something happens and you know the test is going to close or something's going to close, I can always open that up for you. I'm fine with doing that. As long as you have a reasonable explanation as to why you need extra time, a legitimate explanation, I'm happy to keep it open. If there's a technical glitch, I will absolutely keep it open for you. So don't worry about that. So anyway, I hope you do well in the course. If you need help, please take advantage of these resources. And with that, good luck this semester. Thank you very much.